Everyone, welcome to topic 4.5, stoichiometry. So in this, you should be able to explain the changes in amounts of reactants and products based on a balanced equation for a chemical process. This includes mathematical representations. Okay, so stoichiometry is a term used to describe the conversions that involve mole ratios from balanced chemical equations. Before performing any calculation, you must have a properly balanced chemical equation which will ensure that atoms and mass are conserved. Each stoichiometry problem is different, so it is imperative that you read the problem to determine what you are being asked to find out and what you already know. I cannot show you. There is no way that we can look at every single different iteration of a stoichiometric problem in the span of this class. You have to be able to utilize a specific skill set in order to solve these problems, and we're going to go over those here. The coefficients from a balanced chemical equation are used to create the mole ratio, which is the bridge between given quantities and desired quantities. The term stoichiometric ratio means that you have a ratio of moles in the problem that matches the ratio in a balanced equation. In some cases, you will be given information about more than one of the reactants. This signals that you will have a limiting reagent problem. The limiting reagent is the reactant that runs out first, and the excess reactant or reagent is the one that is not completely consumed or you have leftovers. Conceptually, it is often easier to consider how much product each reacting particle can produce separately and then compare the two values. So we are going to first address this method where we look at how much do our starting amounts give us of a specific product. So we're doing double work. We are also going to look at a second process, which is called a Bca table. And we will come back to that. That Bca table will also lead us into a skill set that we need when we discuss equilibrium problems much later this school year. So we'll discuss both, okay? In a lab situation, the predicted amount of product may not be produced, so one can calculate the percent yield by comparing the experimental value to the predicted value. Often, the actual yield is different from the theoretical yield. That is normal. In the lab, the goal is always to get your actual yield as close as possible to the theoretical yield. We use the term theoretical yield or predicted or calculated to describe how much you should be able to make in the reaction. We use the term actual or experimental or actual mass obtained to describe the amount you actually make in the experiment. Percent yield is a way to compare the two, and we use this equation to do that. Okay. Here we have a stoichiometric road map. I know I used this one last year. However, depending on which teacher you had, it may be different. But this is a good one to help you figure out where you're starting and where you need to go and the process you need to use to get there. Okay, you always start on the left and work your way to the right. Okay, and there's some additional useful information there. So an example is provided here. You can look through this at your own time. They also give you a limiting reagent example in here. And notice that for the two amounts given, they show you that you're going to convert both of those to your target amount, which is the grams of rust, which is here. Okay, so you end up with grams of rust. Now the one that you actually make is going to be the smaller value out of the two, which is this one. So you're technically doing the stoichiometric problem twice, one for each given reactant in order to find your correct amount. The smaller the value is the one that is correct. So the 21 grams of rust will form from a reaction between the 15 grams of iron and 6.5 liters of oxygen gas. You could also find out that the iron was limiting reagent and that the oxygen was excess. However, it doesn't tell you directly how much of the oxygen gas was in excess. Okay, you only know that you have some left over. So you would have to do a back calculation to figure out how much is left. And I'm going to show you an easier way to do that. Okay, so for our first idea, what is the percent yield of the reaction between 41 grams of cesium and 13.4 grams of oxygen if 23.8 grams of cesium oxide is collected. Well, the first thing to be able to do any stoichiometric problem is you need to write a balanced chemical equation. So we're going to start with that. So we have cesium, and it doesn't give me a state of matter, but cesium is a metal, so we can assume it's probably a solid. And we're going to react that with oxygen gas, and we form cesium oxide, and that's probably a solid too because it's an ionic compound. Okay? And since it says just oxygen, that is always going to be molecular oxygen, which is O2. And now cesium is in group 1A, so it has a +1 charge, whereas oxygen has a 2-, so we trade the charges to balance their charges out. Okay, so from here we can use the amounts that we're given, which is 46.1 grams of cesium and 13.4 grams of oxygen, and we're going to change it into this one. We're going to use the process discussed in the notes to do this part. Okay, and then I will cover in the next one how we can use a Bca table to do the same thing, but give us a more diverse set of answers that we can use in a wider reaching way. So that way we don't have to do as much work in the front, or in the long run, I mean. A little bit more in the front end, but less in the long run. Okay, so we're going to convert both of these amounts to grams of cesium oxide. So starting with my first one, I'm going to take the 46.1 grams of cesium, and I'm going to first convert it to moles of cesium, because I can relate moles, I can't relate grams directly. So 1 mole of cesium has a molar mass of 132.91 grams. And we'll keep converting this. So moles of cesium, and we want to find cesium oxide, so CS2. We have to go to moles first before we can then take the moles and go to grams of cesium oxide. Okay, the molar mass of cesium oxide from the periodic table calculation is 281.82. And then we get our mole ratio from the balanced reaction, which it is not balanced, so I need to balance it. So I write a 2 here to balance the cesiums. I see I need to write a 2 in front of this one to make it 2 oxygen, but that means I need to update on the other side and make this 4, so that I have 4 cesium on both sides and 2 oxygen on both sides. So now I can put my coefficients in wherever they belong. And so we have 4 cesium is needed to produce 4 moles of cesium for every 2 moles of cesium oxide. Multiplying everything across the top and dividing by the bottom, we see units cancel out, and our units are grams of cesium oxide, which is what we should get. And then we're going to plug the math in, and you should get 48.9 grams of cesium oxide. Now this is just for one reactant. I need to do it for the second one. So I'm going to repeat this process with the mass given of oxygen. So 13.4 grams of oxygen, O2, and I'm going to change that into moles of O2 using the molar mass. And the molar mass of oxygen is 32 grams. And then I can change the moles of oxygen to moles of cesium oxide using the mole ratio, which is 2:1. And then from there, I can change the moles of cesium oxide to grams of cesium oxide using the molar mass of cesium oxide that I calculated previously. Okay, so using the same process as above, I'm going to multiply the top and divide by the bottom, canceling units as appropriate. And you should end up with 236 grams of cesium oxide. Now I have these two amounts. My reaction can only make as much as my smallest amount, which is going to be my cesium. So I'm limited to this amount, 48.9 grams, because I will run out of cesium before I run out of oxygen. And that's what these two tell me, is that the smaller amount is the most I can make, because otherwise I'm going to run out first. So now I will use this as my theoretical because it is my calculated value to determine the percent yield of this reaction. So percent yield is my actual, which is 28.3 grams of cesium oxide, and I'm going to divide by my theoretical, which is 48.9, and multiply that by 100, so I get a percent, and you should get 57.9%. Okay, so this is the process where we take and we convert to a reactant, okay, and then or a product, sorry, we convert it to a desired amount, and that gives us a theoretical yield based off of a limiting reactant. However, sometimes we want to know how much is left over or some other things. So Bca tables tend to be more diverse, okay? So the first thing you have to do for a Bca table is the same with anything, is write the balanced reaction. So we're going to write our balanced reaction. So we have iron 3 chloride, so FeCl3, and it's got a concentration, so that tells us that this is an aqueous solution. Is reacted with sodium carbonate, so Na2CO3, and it also has a concentration, so that's aqueous, and it's going to produce something. Well, we can use our double exchange reaction pattern to switch the cations, and so we end up with sodium chloride, and both of those have a magnitude of 1 charge, so +1 and -1, so they cancel, so I don't need to trade the charges to balance them, and they're going to have a state of matter, plus iron and carbonate. Now iron, it tells us, has a 3+ charge, and carbonate is one of those you should remember is 2-. So we're going to trade those charges so that they balance. So we have 2 and 3. Okay, and that's probably going to be a solid. This is aqueous because it's salt in water, so salt water. So now we can balance. So I'm going to start in the front, and I see you can do the full like atom inventory, but I'm going to just balance it real quick for the sake of time. Going through this 2, and then I see I now need 6 chlorine, so I'll write a 6 here, and then I need a 3 over here, and I check 2 irons on both sides, 6 chlorine on both sides, 3 times 2 is 6 sodium on both sides, and 3 carbonate on both sides. So this is now balanced. So now I'm ready to start my calculations. Because I have a balanced equation, I can now start going. So start with your balanced equation. Your next step is to convert anything to moles. Okay, so we are given a volume and a concentration, so we can either use the molarity equation or just convert it and use molarity as if it's a conversion factor to figure that out. So for the first one, we have 50 milliliters of iron chloride, and I'm just going to convert these, so 1,000 milliliters and 1 liter, and then I'm going to use my molarity here in this fraction to change it to moles. So I need liters on the bottom, and I want moles on top. Okay, and from my molarity, I see that every 1 liter has a molarity of 0.250 moles. And that's what molarity means, is that many moles will be present in 1 liter. And so we run that math, and we should get a value of 0.0125 moles of iron 3 chloride. We're going to repeat this process for sodium carbonate. So we are given 50 milliliters of sodium carbonate, and they are so nice to us that they give us the same volume and concentration of both the reactants, so that makes the math a little easier. That is not always going to be the case. So we end up with the same amount of moles of both. Okay, now for Bca table, we need our balanced reaction. So I'm going to rewrite it so I can, pardon me, so I can easily use it. So I'm going to write 2 iron chlorides. And for this, I don't need the state of matter, so I'm going to omit it for the sake of simplicity. And I'm going to draw a big line so that way I can show how I'm separating these. Plus 3 sodium carbonates yields 6 sodium chloride plus iron carbonate. Okay. So Bca means before, how it's changing. So before it reacts, what do I have? How it's changing. And then how much do I have after? And we should see that B plus C should equal A. Okay. So setting up the table, you write your Bca, and I always put a double line under the arrow, and then single lines under the plus signs, so that way I separate them out. Next, I'm going to fill in my before amounts. Before I react anything, I know that I will have 0.0125 moles. All of these values are in moles. So I'm not going to put units in here because that's just a lot of writing. So I have 0.0125 moles of both reactants. But I haven't reacted anything or combined them, so I know I'm not going to have any products. So those will be 0. How things are going to change is going to be based off of the mole ratios. So I'm going to bring those numbers down. Now reactants, I lose them or use them, so I'm going to put minus signs. And I'm going to put a parentheses as a placeholder. I forgot a 6. So that way I know that there is going to be some number that's going to go in here to make the math work out. Okay. Now I'm going to ignore my products for right now because I need to figure out which reactant is going to hit 0 first. So to do that, I'm going to do 2 goes into, I'm going to pretend that they're both going to be equal to 0, and I'm going to figure out what number has to go in the middle here to make that happen. So for this one, it would be 0.0125 divided by 2, and over here is 0.0125 divided by 3. Looking at these two, this first one is equal to 0.00625, and the second one is equal to 0.00417. Okay, the one, just like before, that is smaller is limiting, but now I'm not taking it all the way to the end. I'm focusing on just the reactants, and then I can go further once I know which reactant is going to limit my reaction. So I'm going to use this. This is what goes in my parentheses. So based off of which one will get me to 0 the fastest based on its smallest amount, that goes in all of the parentheses. Okay. And now I will simplify all of my numbers. I know this one has to go to 0, and then 0.0125 minus 2 times my parentheses number gives me 0.00416. And then coming over to the other side, this is 6 times the 0.00417, which is going to be 0.0250, I think. I'm doing the math in my head, so don't trust me. And then finally, this last one is 0.00417. So I now figured out how much I have left over of one of my reactants and how much I make in moles of both my products in one little table setup. So I get a lot of information from it. What I wanted to know specific is at the end how much I have left over. So I would circle this and maybe write I have 0.00416 moles of iron chloride, because that's the column it's in, left over. It doesn't say convert it to grams, So unless it explicitly asks, you can leave it in moles, but I will leave it here, and you guys can convert it to moles by multiplying by the molar mass of iron 3-chloride. Okay, we will do additional practice problems like these. I will probably, I'm looking at my answer key. For the most part, I do the Bca table, but I only do the components that you need to solve for when I am showing them. So check your work as you go, and our end answers will always be the same, even if you use this method that we saw in the I do, or if you use the Bca table method that we went over in the we do. Okay, so please practice these problems, check your work as you go, and thank you for tuning in.